All right, I hope you guys are all doing well, and we'll get started here. And so today I'm going to continue our lecture where we're going to finish the back propagation. Okay, and so on Friday we worked through back propagation. To figure out the derivative with respect to the second weight matrix. Okay, so here again, this is kind of where we are, is that we are doing neural networks. On Wednesday, we talked about forward feed, and we said, you know, you're going to start off with your x values here. You multiply your x values by your W matrix, these weights, which these arrows represent the different weights, and that's going to produce your Z matrix. We apply an activation function onto Z, and then we multiply the results with another matrix W2, and that gives us our other Z matrix. We apply the activation function on this Z matrix, and this gives us our predicted values Y hat. Okay, and that's what we've got here. We've got X times W1 gives us Z2, F on Z2 gives us A2, A2 times W2 gives us Z3, F on Z3 gives us Y hat. So our Y hats can be summarized like this. And what we want to do is we want to minimize the difference between our predictions Y hat and the actual values Y. So we want to say, okay, here's the actual values Y. Here are my predictions Y hat. And I want them to get as close as I can possibly get them. We want to minimize the squared errors, right? So we're going to say our loss function is our mean squared error here. We take the difference between this and this, and we square that difference. We sum them up and divide by n. That's our loss function, okay? Now, just to kind of simplify things later, we converted our loss function just by multiplying it by a constant, okay? So we're going to call this j instead, all right? And we keep in mind that to calculate our loss function, we need to figure out our Y hat values. Our Y hat values are found by doing X times W1, apply the function on that, multiply that by W2, and apply the function on that, okay? So we need to calculate, in order to evaluate our loss function, we need to calculate our Y hats, okay? And what we want to do next is we want the gradient. We want to see how much does our loss function change with respect to our two weight matrices. We want the gradient with respect to W2. We want the gradient with respect to W1, okay? Now, normally in calculus, you just find the derivative and you'd set it equal to 0 and you'd solve. We're gonna do something similar, except we're not gonna be able to set it equal to 0 and solve. So we're gonna find the gradient, but then we're gonna use gradient descent. We're going to find the gradient, and then we use gradient descent. So that means we start off at some location, and with gradient descent, we're going to find which way points in the steepest descent, and we move in the opposite direction. That should give us downhill. Okay, and we take a step down. Then we find the gradient again with the point somewhere in the uphill direction, and then we're going to move in the opposite direction to go downhill. And we're going to do that over and over and over again. And hopefully, if we do that, that should get us to like a local minimum, some kind of low area, or at least a flattish area, to kind of indicate that we've reached a minimum here. Okay, so this is our plan. Okay, and on Friday we worked through this for the second weight matrix, kind of the first gradient that we could find. All right, and then we said, well, the second weight matrix is a 3×1 matrix, and therefore the gradient of the loss function with respect to W2 is going to be a 3×1 matrix. The gradient of the loss function with respect to W1 has to be a 2×3 matrix, because W1 is a 2×3 matrix, okay? And then we worked through this. I'm going to kind of skip through all of that stuff. And on Friday, this is where we ended up. We said the gradient of the loss function with respect to W2, so dj dW2, is going to be A2 transpose multiplied by delta 3, where delta 3 is this thing, Y minus Y hat, that's an n×1 matrix, element multiplied by F prime on Z3. Okay. Is that all right? Do you guys feel okay with this? So this is where we left off on Friday, right? Okay, and so today we're going to continue this out, and we are going to find the gradient with respect to the first weight matrix. So we're going to keep working backwards, and we're going to keep saying, okay, we're going to work backwards to find the gradient with respect to the first weight matrix, and the hope is that once we have that gradient, we'll be able to minimize. Okay, so so when we do this, the beginning part is the same steps as what we did on Friday. So on Friday, we were finding the gradient with respect to the second weight matrix. The beginning part's the same, okay? We're finding the gradient with respect to the first weight matrix, and we work backwards like this, okay? We're gonna do, here's our loss function, 1/2 sum of y minus y hat squared. You take the derivative of that, and the square comes down and it cancels out with the 1/2, and we get y minus y hat. And then we have to apply chain rule. So y hat has a negative, so we're going to multiply by negative, and we're going to say, well, how does y hat change with respect to W1? Okay, so we say, well, y hat changes with respect to W1 via Z3. And so we say, well, how does y hat change with respect to Z3? And then how does Z3 change with respect to W1? So the way y hat changes with respect to Z3, that's going to be f prime of Z3, where f prime is the derivative of the sigmoid function, okay? So f prime is the derivative of the sigmoid function. So this is where we are, and we want to say, okay, well, how does Z3 change with respect to W1? All right. So if we look back to this, we say, well, Z3 is the result of the activated values multiplied by the second weight matrix, okay? So we can say, well, Z3 is the result of the activated values A2 multiplied by our second weight matrix W2, and therefore, what we're going to do is we're going to say, well, how does Z3 change with respect to W1, okay? Well, Z3 changes with respect to W1 because W1 influences the A2 values. W1 does not influence the W2 values. W1 only influences the A2 values. So we say Z3 changes with respect to A2, and A2 changes with respect to W1, okay? So how does Z3 change with respect to A2? Well, we say Z3 is the result of A2 times W2. Therefore, the derivative of Z3 with respect to A2, or the gradient of Z3 with respect to A2, is W2 transpose. Okay. So last class people said I was going too fast. So I want to take a pause here and just make sure that we understand what I'm doing here, okay? Or I'm basically kind of doing calculus, and I'm saying Z3, how does Z3 change with respect to W1, okay? It changes because W1 influences A2 and A2 influences Z3, right? So we're kind of splitting up these derivatives here. And we say, well, how does Z3 change with respect to A2? Z3 is the product of A2 times W2. So how does Z3 change with respect to A2? It's going to change basically its rate of change is W2. But in order for the dimensions to be correct, because A2 is a 1/3, we take the transpose of this. Right? And that is, if you check your notes from earlier on in the course, when I think I have a table in one of those lectures showing gradient relationships. It will show basically this relationship. Okay, I hope that's okay. One of you gave me a green check mark, so, but I hope the rest of you are also doing okay. So we're going to say Z3 with respect to A2, derivative of Z3 with respect to A2 is W2 transpose. We're going to put that, we're going to replace this with this. And so now we want to find how does A2 change with respect to W1, okay? Notice that as I'm working, I'm always writing the dimensions of these things underneath my elements, okay? I'm writing the dimensions of each of these things because you want to make sure your dimensions align, all right? Because when you try to put this into code, which we're eventually going to do, if you don't have your dimensions right, you're going to keep running into dimension mismatch errors. So always do your work on pen and paper, with pen and paper, and write your dimensions underneath, and that will really guide you and help you when you have to code these things up. Okay, so how does A2 change with respect to W1? Okay, so again, just like before, A2 is the result of applying F prime to the Z matrix, okay? So we're gonna say A2 changes with respect to Z2 matrix, and we can say Z2 changes with respect to the W1 matrix. All right, so we split this apart, okay, using we further split the derivative. And we're going to say, because A2 is the result of applying the sigmoid activation function, the derivative of A with respect to Z2 is the derivative of the function F. So this is going to just be F prime of Z2, okay? So I hope this part's okay, right? So derivative of this with respect to this is just going to be F prime of this. So I put that in there. So here we are, okay? So I've got a 1 by 1 multiplied by 1 by 3, and I got a 1 by 3 here, okay? Because we're just looking at one element. So Z2 sub n, right? Z2 is an n by 3 matrix, but we're only looking at one row. We're just thinking of how this works for one observation. And for one observation, it's going to be a 1 by 3. All right, and okay, so here is the last thing we need to figure out, okay? So Z2 for row n is a 1 by 3 matrix. Okay, I've got a 1 by 3 matrix. And I want to say, well, how does this change with respect to W1? So W1 is a 2 by 3 weight matrix, remember. So here's a, right? So we're asking, how does these values, we've got one row of 3 Z values. How does that one row of 3 Z values change with respect to all 6 of these weights? Right? So we've got a matrix of 6 weights, a 2 by 3 matrix here. Okay, we've got this 2 by 3 matrix. We're asking, how does that change, or how did the Z elements change with respect to that 2 by 3 matrix? It feels weird, okay? It feels weird. But if we look at the multiplication between one row in X, okay? X is a n by 2 matrix, and if we look at just one row in X, and we say, okay, we're going to multiply this one row in X by this 2 by 3 matrix to give me a 1 by 3 matrix, and we look at how the elements in Z change with respect to W, I think it will make a little bit of sense. So I've kind of tried to color code these things. So I've got, these are my 6 elements in W, and this is my one row in X. My one row in X multiplied by this 2 by 3 matrix results in this one row in Z, okay? So I've got a 1 by 2 matrix here, and I've got a 1 by 3, okay? There are 3 terms here. Here's one term, here's the middle term, second term, and here's the third term. And let's look at how these values change. So I've got in the first element, okay, it's going to be the first X, the X1 value multiplied by W11, okay, and the X2 value multiplied by W21. And then for the middle element, I've got the X1 value multiplied by W12, and the X2 value multiplied by W22. And then for the last one, I've got the X1 value multiplied by W13, and the X2 value multiplied by W23. And this is a typo, this should be a 2, okay? Not a 1. So this is W23. So here, I've got my 3 elements, and so let's just kind of think about, like when you do your numeric gradient check, so in your homework this week, or the one that's due today, you had to do some numeric gradient calculation, right? And the way you calculate your numeric gradient is you you add like a tiny little value to one of the things, and you say, well, how does this change the result? How does this change the result? Okay. So if I add a tiny little value to say this first element, this top element, W11, how is the result going to change? Well, it's going to change by a factor of x and 1. Okay, it's going to change by this because W11 is being multiplied by x and 1. If I change this value right here, this middle value on the top row, by a factor of epsilon, how does the result change? Well, it also changes by x and 1 because x and 1 is being multiplied by that top row. Right? Any value I change in the top row is going to get multiplied by x and 1, so it's going to get changed by x and 1. Any value I change in the bottom row is going to get multiplied by x and 2. So really, there's only two things that change. So you change any value on the top row and it changes by this. Change any value on the bottom row and it changes by this. So the partial derivative of z2 sub n with respect to W1 ends up being a 2 by 1 matrix. Okay, it's just going to be the transpose of xn1 and transpose of xn, which is going to be kind of a 2 by 1 matrix with the elements xn1 and xn2. All right, I just kind of want to pause there and ask if that makes sense when I'm trying to argue here, that the gradient of a 1 by 3 matrix with respect to a 2 by 3 matrix ends up being a 2 by 1 matrix. So the dimensions feel so crazy, but if you pay attention to how the multiplication works, I'm hoping it makes sense here. All right. So we're going to say that the gradient of z2 sub n with respect to W1 is going to be xn transpose, which is a 2 by 1 matrix. So I'm going to put that back into here. And then when we look at this, we go, oh my goodness, the dimensions don't line up, right? So we look at this, these dimensions don't line up. I have the different pieces. These are the pieces that I need to multiply together, but the dimensions don't line up. Okay, so what can I do? Well, we know that the result, this result, what is the result it has to be? The result has to be a 2 by 3 matrix, right? Because W1 is 2 by 3, and the gradient of this loss function with respect to W1 needs to be a 2 by 3 matrix. So I'm going to kind of rearrange a couple terms, okay? I'm going to bring this around to the front, okay? And then, so I've got a 2 by 1 here, multiplied by this 1 by 1 scalar. And then these two elements, this is a 1 by 3 matrix, and this is a 1 by 3 matrix. And so to multiply them together, I'm going to do element-wise multiplication. And this will keep it a 1 by 3. And so these combine to be a 1 by 3, whoops, yeah, a 1 by 3, and this result will just be a 2 by 3 matrix, okay? So if I do 2 by 1 times a 1 by 1, this is a 2 by 1 multiplied, I multiply these two together and they get a 1 by 3, and the result is going to be a 2 by 1 times a 1 by 3, which results in a 2 by 3 matrix, okay? And that makes sense. We want to say, how does the result J, how does the loss change with respect to W1? It's going to change with, if the result's going to be a 2 by 3 matrix. And basically every element, right, so this has a subscript of n, so every element is going to produce a 2 by 3 matrix. And the total gradient is going to be the sum of every single one of these 2 by 3 matrices. So you can imagine kind of these different sheets, these 2 by 3 sheets laid on top of each other and added together or something. Okay, that's going to be the result here. All right, this is what we had at the bottom of the previous page, and we can ask, well, can I get rid of this summation sign, right? I got these subscripts n, okay? So this is the derivative or gradient with respect to W1 for one element. But what I want to do is let's see if I can do it for all, right? I don't want to have to do it for each one and then sum it up. So can I get rid of the summation? Okay. Well, if I get rid of the summation, what happens? Okay. Everything that has a subscript n becomes a something by n dimensional, right? So xn, if I get rid of the x, becomes x, which will become from a 2 by 1 becomes a 2 by n matrix, okay? And then here my y's become the matrices y, and that's going to become an n by 1 matrix, okay? So used to be a scalar, this becomes an n by 1 matrix, and f prime of z becomes an n by 1 matrix as well. So I have to matrix element-wise multiply there. W2 remains a 1 by 3 matrix. There's no change there. There's no subscript n there, so it remains 1 by 3. And then Z2 sub n is a 1 by 3, and if I get rid of the subscript there and I expand it to the entire matrix of Z, I get an n by 3 matrix. So this is what I have. And let's see how we can multiply these together, okay? So I'm going to multiply this n by 1 and this n by 1 using element-wise multiplication. And we're going to call this delta 3, okay? And so here I have an n by 1 matrix multiplied by a 1 by 3 matrix. And we're going to multiply these two together. So these two, when I multiply these two together, I get an n by 3 matrix here. And if I have an n by 3 matrix here, I can multiply that by this over here, which is also an n by 3. I can do element-wise multiplication. So this times this over here becomes an n by 3 matrix via element-wise multiplication, right? So element-wise multiplication means you have two matrices of the same size, and you're going to multiply, line up each thing and multiply them together. And X transpose is 2 by n. And so I can multiply this 2 by n matrix by this n by 3 matrix, and the result is going to be a 2 by 3 matrix. All right. And so again, if I did not write the subscripts under each of these things, I would just have like an X and a W and a Z, and I would, you know, when you have an X and a W and a Z and Y's and things like that, there's a temptation to treat them just like univariate variables, like in calculus, and you can just like move them around, and you're not scared. But you should be a little bit scared and respect these dimensions, because it's very important, right? And so if you don't, when you try to enter this into R and you try to multiply these things together, you're just going to get dimension mismatch, error, dimension mismatch, error, dimension mismatch. And so by taking the time to write the dimensions underneath each element and doing the math and doing the work there, you can kind of respect the dimensions that exist. And then when you code them into R, you're not going to run into these problems here. Okay, how does this feel? Give me a green check mark if this feels okay, or some other kind of feedback if you're not feeling good about it. Let me give you the first quiz answer. First quiz answer today is the letter E. E as in elephant. E as in elephant. First quiz answer today. E as in elephant. Okay, only about half of you are giving me a green yes. Okay, a few more of you. Thank you. If you guys have questions, don't hesitate to raise your hand or ask in the chat. Because once we have this, I'm going to start to code it. Okay, so it says, as a general rule of thumb, is it that if matrices and vectors can't be multiplied together, then we multiply them element-wise, assuming we do the math correctly. So you have to kind of think, right? So all of this, basically applying chain rule, and we're doing all of this multiplication. So we know that these elements have to be multiplied together in some way. You will use matrix multiplication or element-wise multiplication. So always have in mind the shape that your result needs to be in, right? So you think, okay, the result I need has to be a 2x3 matrix, right? So we keep that in mind. That's going to be one of our guiding principles. And then the other part is we say, okay, well, I've got these terms, right? I've got an n by 1 and a 1 by 3. Well, those combine to an n by 3. And then, so here, you know, when we have something like this, we have a couple choices, right? I can do an element-wise. I've got an n by 3 here and an n by 3 here. If you have n by 3 and n by 3 here, you can do element-wise multiplication, and that will preserve it as an n by 3, which is what we want to do, right? The other choice is I could transpose it, and I can do an n by 3 transpose times an n by 3, and that will produce that will be 3 by n times an n by 3, and that will produce a 3 by 3, okay? Or the other option is you can transpose the other, and you'll go from an n by 3 times a 3 by n, and you'll get an n by n result. So you always kind of keep in mind what's the result that you want, and you say, well, do I want a 3 by 3 or do I want an n by n? And that will also help you guide you as far as which thing to transpose and how to multiply these things together. So in this case, we want the result to be 2 by 3, and if we pay attention to this, we can say, okay, well, I've got an n by 3 here and an n by 3 here. It makes sense to multiply these element-wise, right? If I tried to do it like back here, if I didn't, and I had this 1 by 3 and an n by 3, you know, I wouldn't be able to do element-wise multiplication there. I've got to kind of I have to multiply this over here first to make it an n by 3 before I can do element-wise multiplication. So you got to kind of pay attention to the dimensions, ask yourself, where is it that you want to be headed, and you try to move your elements in a way that works out that way. All right, so coding it up. Let's code this up, okay? First, I'm going to just write a couple functions. Well, I'm going to just write this function that's going to calculate the sigmoid. 1 over 1 plus e to the negative t. I have, for whatever, a function of z, 1 over 1 plus e to the negative z. No surprise there. All right, here we've got just our data, input data x, right? So I think we said 3 hours of sleep, 5 hours of study resulted in a test score of 75. 5 hours of sleep, 1 hour of study resulted in a test score of 82. 10 hours of sleep and 2 hours of study resulted in a test score of 93. Okay. And what I'm going to do is I'm going to just kind of scale all of these values. Okay. And the reason for that is if we look at the sigmoid function, one problem is that if I go out to some big number like 20 or 100 or something, right? So if I'm using values like 75, 82, 93, basically it's super flat, right? It's asymptotic. The function out there is very flat. There's pretty much no, like if I calculate the derivative there, it's going to be very close to 0, okay? Because it's pretty much asymptotic. So the derivative is going to be pretty much close to 0. Same thing with super negative numbers. I'm going to get a derivative that's very close to 0. So what I'm going to do is I'm going to scale these down to kind of just bring them into some range of between like 0 and 1 or -1 and +1 or something, basically in this realm. In this realm, there's a derivative. The derivative exists, okay? The derivative is a number that's not 1, or not 0, okay? Out here, it's super flat. Derivative is 0. Down here, it's also super flat. Derivative is near 0, okay? That's actually one of the biggest reasons why the sigmoid function is no longer popular, is that there's only a sweet spot where there is a derivative, and for many other values, the derivative is 0, which can lead to problems. So we scale these. So we're no longer 75, 82, 93. It's going to be 0.75, 0.82, 0.93. Okay, and then just to kind of keep my code a little bit flexible, I've posted this code on CCLE, by the way. Okay, so if you go to the class page, there's neural network example code, and that's pretty much all of this code here. I have these variables, input layer size and output layer size and hidden layer size. So rather than hard coding the W1 matrix as being 2 by 3, I'm going to say the W1 matrix is input layer size by hidden layer size. Okay. All right, so let's just review how forward feed works, right? So we do x times w to give us our z values. That's, let me come back to this picture, right? We have our input matrix x. We're going to multiply it by our w matrix, and that gives us our z values, okay? So that's x times w is z. And then we apply the sigmoid function, the activation function, to z. That gives us our activated values a. Then I take those activated values from here and I multiply it by our second weight matrix W, and that gives us our matrix Z3. Okay, so I do A2 times W2, and that gives us Z3. And then we apply the activation function on Z3, and that gives us our Y hat. Okay, so when I code this up, it looks exactly that way, okay? Here's our, I define my matrices, W1 and W2. Input layer by hidden layer is W1. W2 is hidden layer by output layer. So that's W1 is 2 by 3 and W2 is 3 by 1. All right. And this is just forward feed. X times W. W1 is Z2. That's exactly what I have here. X times W1 is Z2. Apply the sigmoid function onto Z2, and that gives us A2. That's exactly what I've written here. A2 times W2 is Z3, and apply the sigmoid function to Z3 to give us Y hat. Okay, so whoops. So that's exactly that, all right? So this just is forward feed, and this gives us our Y hat values. Okay, so now that I have my Y hat values, I want to be able to calculate my cost function. How much loss do I have? So I'm going to take the difference between Y and Y hat, the actual values of Y. The actual values of Y and our predicted values Y hat. So the previous slide shows us how we got our Y hat values. Now we're going to take the difference between Y and Y hat. We're going to square those differences and add them up. And when I do that, it tells me my current cost is 0.015, 0.015, which doesn't sound like a lot, but it's actually quite a bit. Considering all of my numbers are less than 1, I'm getting a fairly significant amount of error here, okay? Okay, and then, all right, so now we want to find the gradients, right? And so the gradients, to find the gradients, it involves things like f prime, sigmoid prime, so the derivative of the sigmoid function is this. And the first gradient that we calculated was dj dw2, the derivative of the loss function j with respect to the W2 matrix. And that gave me A2 transpose times delta 3, okay? Where delta 3 is y minus y hat, element-wise multiply by f prime of z3, okay? And that's exactly what I code here. I write delta 3 is y minus y hat times sigmoid prime of z3. And then I have the transpose of A2 transpose, matrix multiply, A2 transpose, matrix multiply by delta 3. Okay? And again, I can confidently do these operations because I took the time to write my dimensions underneath, and so I don't have to worry about the dimension mismatch errors right now, right? All right, so I'm just going directly from what I did, the math results, to a code result, right? All right, and then now we want the derivative with respect to D1, or W1, the weight matrix one. So we got dj dw1, and the result of that, okay, is x transpose times delta 2, X transpose times delta 2, where delta 2 is equal to all of this. Delta 3 times W2 transpose, element-wise, F prime of Z2. So I have my earlier result, delta 3. I'm going to do matrix multiply that by W2 transpose, delta 3 matrix multiplied by W2 transpose, and element-wise multiply by sigmoid prime of Z2. Okay, sigmoid prime of Z2 gives me that, and this gives me exactly what I want. And then the result, dj dw1, is X transpose times delta 2, matrix multiply delta 2. All right, and so that gives me dj dw1. So that works. All right, and okay, so let's not lose sight of where we're going. All right, so we have found the gradients, and we've coded our gradients up in our computer. All right, and the reason why we want to find our gradient is so that we can do gradient descent. Right, so we're going to start off because we want to find a local minimum. Right, we want to find where our loss function is minimized, and that's going to be where our gradient is flat. Okay, and so we're going to just start off at some arbitrary location, and using gradient descent, the gradient descent will say, okay, this way points up, and we're going to take a step downwards, and we're going to keep taking steps down the hill until our steps downhill end up being pretty flat. Okay, and that should get us to a local min. So that's what we're doing here. Okay, so I'm going to just start off at some arbitrary location. All right, and so I just use some random uniform values. I got 6 random uniform values for my W1 matrix, 3 random values for my W2 matrix. All right, and then this is not necessary, but just for illustration, I'm going to keep track of my cost function. I want to see how the values change. Okay, and this is my learning rate. The scalar 5 as a scalar. This is just going to be my arbitrary learning rate. Okay, and this is gradient descent. This looks like a lot of code, but it's not too bad. Okay, there's basically 3 pieces here. So don't, first part is forward feed. Okay, we're gonna go from our x's to our y hats. So this first part here, what's going on? This first part is just doing the forward feed. We're going to do x times w gives us z. Sigmoid on z gives us a2. a2 times w2 gives me z3. Sigmoid on z3 gives me y hat. So this is just calculating my y hat. So it takes my current values of w1 and w2, and it says based on your current values of w1 and w2, these are the y hats you're going to predict. Okay? Because I need to know what my y hats are in order to get my gradients. Okay? I take my current values of y hat and I calculate the cost. And I say, well, what's the difference between y and y hat? And I store that here. Okay, this line is not necessary, but I do it for illustration. And then the next part is once I get my y hats, which I need, okay, I calculate my gradients. Okay, I find dj dw2, the gradient of j with respect to w2, and I find dj dw1, the gradient of j with respect to w1. Okay, so I say, well, how does this change with respect to w2, and how does it change with respect to w1? So this is my these are my gradients. So first I find my y hats, and now I find my gradients. Okay, and this is all of gradient descent. Okay, gradient descent just says take your current value of w1, and then subtract off a scalar times your gradient, right? So you just take your current value and subtract off the scalar times the gradient. And that gives you the value that you're going to use next, okay? And we do this for both W1 and W2 because I've got 2 matrices to alter. So I have, they each have their own gradients, okay? And that's the entire gradient descent algorithm, okay? All right. How does that feel? Does that feel okay? Let me give you the second quiz answer, and if it feels okay, give me a green check mark. The second quiz answer today is A. A is an apple. A as an apple. How did I choose the scalar 5? That was completely arbitrary, okay? It's a lot of guess and check. There's not a good system for figuring out your learning rate, okay? You know, I took an online course, or at least I watched these on, didn't actually take the course, I just watched the available videos, okay? So Stanford had a course on neural networks. And their strategy was try out a whole bunch of different learning rates in the beginning and just do a few hundred iterations. Do a few hundred iterations with this learning rate, a few hundred iterations with a different learning rate. Try a whole bunch of them and look at your cost function and see how your cost function behaves with different learning rates. And then and try to go from there and pick a value that seems to work well. Because if you pick a learning rate that's too big, your cost function is going to have a crazy bad behavior. If your learning rate is too small, your cost function will change too slowly. But apparently, it's a thing, and I don't know. There's like there's a blog showing crazy cost functions. I don't know. Okay. All right. I don't know. Loss functions. Okay. So this is like super old, no longer a thing, but there's a Tumblr. Tumblr's lost these days, but these are how just loss functions. So what you want to see something go down, okay? You want to just kind of keep, you want to see the loss go down, right? But here something happened, right? It goes down, 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 and then it goes crazy, right? So these are all things that like you don't want to see these things, but I guess it was funny enough for people to submit to the blog. Okay, but yeah, how do you choose a scalar 5? I don't know. All right, it's arbitrary. I think I played around with it, and 5 seems to work out well. Okay, so when I run this, I run it for what, 10,000 iterations. Okay, that's just an arbitrary number as well. And these are the resulting coefficients for W1 and W2. Completely arbitrary. These, not arbitrary, these are the results that will give us a low cost function, but these are uninterpretable. I have no idea what any of these things mean. Unlike linear regression, where you can say the slopes actually have meaning, here these W weight values don't have meaning here, okay? But we look at how well we predicted our values. So here's our target values. Our target values are 0.75, 0.82, 0.93. And what did we predict? We predicted pretty close numbers, 0.749998, 0.8200548, 0.9298944. So our predictions are pretty close to the actual values, okay? So I guess we should feel good about that. Certainly we're overfitting because we only had 3 observations and I had 9 parameters to play around with. So I'm like guaranteed to, like, if I tweak them long enough, I can probably get these exactly. If you have 9 parameters to mess around with and you only have 3 observations, surely you can find kind of a set that works. Okay. Here is what the loss function looks like. Okay. So it drops down dramatically. Okay, it slows down for a little bit. It kind of hits this flattish region. And then around the 2000th iteration, it finds another drop. And then from here, you don't get too much more improvement. Probably each iteration reduces it by a factor of like 5% or something like that. And so if you look at the log of the cost history, okay, we see huge drops here. Again, there's that flattish region. where there's very little change. And around the 2000th iteration, it drops off again. And then here, it's this straight line indicates that we're reducing our cost by a constant factor. So we're multiplying by we're probably knocking off around 10%, 5%, 10%, 2% with each iteration. So and it's a constant rate, whatever it is. All right. On Wednesday, you guys have an exam. So on Wednesday, we'll see you for the exam. Just choose whether you're going to take it at 10 a.m. or 10 p.m. If you're going to take it at 10 p.m., don't log in at 10 a.m., okay? I'm going to be checking the CCLE logs and stuff. So don't log in. Well, certainly, I guess you can log into CCLE, but don't download the don't download the 10 a.m. exam, okay? That's a problem. If you download the 10 a.m. exam, you got to take the exam at 10 a.m., right? So don't do that. But yeah, okay, so good luck as you study for Wednesday's exam. And then on Friday, we'll come back and do the neural network stuff, and we'll apply it to like an image database of handwritten digits. I think it's a classic example here. It's going to be pretty cool. So we'll see you on Friday. Good luck, and or see you on Wednesday for the exam. Good luck as you study, and then we'll see you on Friday. All right. Have a good day, and we'll see you later.